And today I will talk about statistical flow data analysis. And here are my collaborators, Sakajo from Kyoto University and Tomoki from Saitama University. And I will talk about several topics, so I have other collaborators as well, but okay, they are main collaborators. Thank you for the invitation to this WPI-SKCM² seminar. Yeah, I really thank the organizers, Kotori-san, and all this institute secretaries, staff members. Yeah, ideally. Yeah. Okay, so let me start my talk. Okay, so what is TFDA? Well, TFDA is the abbreviation of Topological Flow Data Analysis. And so what is topology? I think many of you are not mathematicians. So briefly speaking, so when mathematician says a topology, so it refers to a rough shape. Roughly speaking, the topology is shape. Okay, so for example, so let's say we have a circle and we have an ellipse. Then their topologies are the same. So we do not consider any other geometric information like curvature or arc length or area or such kind of quantities are not considered in the context of topology. For example, in this case, just a number of connected components or number of link structure are considered. And we mathematicians often identify these two objects. Or for example, let's say we have a coffee cup and donuts. So this is the topology. And we apply this concept of topology to the fluid dynamics. So in fluid dynamics, there is a term streamline. So streamline is like this. So we have a flow. We draw a curve that tracks the fluid particle. So we have this fluid particle. It goes this way, right? So this is called a streamline. And we consider the topology of streamlines. So this is topological flow data analysis. We consider topology of streamline plots and then apply it to data analysis. Data analysis way. Okay, so anyway, so here is a background of topological flow data analysis. First, Professor Sakajo and Yokoyama have proposed flow classification theory, mathematical theory, in 2013. And they classified two-dimensional incompressible fluid using word representation. And thereafter, they also proposed three versions as well. So their classification theory is based on the viewpoint of dynamical systems from mathematics, I mean. And in their theory, so they encode the topology of streamlines. I mean, we look at streamline plots and then convert it into unique tree representation. But there was a big issue in their preceding works. So in their preceding works, the conversion of conversion from topology of streamlines to unique representation was done by their hand and the human eyes. I mean, let's say we have a streamline plot. It's printed on the paper, physical paper, and they look at this streamline plot, and then they convert the plot. They convert this plot to a unique representation by following their theoretical definition. And this computation was not implemented on the computer in the preceding study. So I joined the collaboration, and then I and Sakajo and Yokoyama have implemented the computation algorithm in 2019. So now we have a software that achieves automated conversion from streamline data to unique representation. So why we consider topology of streamlines? Well, in certain scenario of fluid dynamics, often streamline patterns play a very important role. So this is an example from their paper, their preceding paper, and this is this figure illustrates the streamline plots and their unique word representations. So here is a wing of airplane, and it's built from the this is a two-dimensional section of a wing of an airplane, and so there is a uniform flow this way. Uniform flow is coming from left to right, and this is wing. Then there are some vortices here. Yeah, you see some vortices here, and in such aerodynamics, vortices play a very important role. I mean, it affects lift drag ratios. So this is a plot of lift drag ratios of the airplane. I think this is a simulation result, numerical simulation result. But anyway, and this pattern, lift drag ratios pattern and topological patterns actually correspond. So in such a way, sometimes topological classification of fluid flow play very important role. So we are considering this topological analysis. Okay, so let me briefly show you a table of contents today's talk. So first, I will show you a quick review of topological flow data analysis. And I think I don't have enough time, so I do not talk about computation algorithm, but I will show you just definition of tree representation. And then I will show you two or three applications of our topological flow data analysis method to meteorology and oceanography, and if I have enough time, then yet another application as well. So anyway, so first chapter, first part of the talk is based on this paper, but basically this paper is regarding algorithm, conversion algorithm. So today I do not talk about the algorithm in detail, so I just show you just the definition of tree representation of fluid. So let's say we have a structurally stable Hamiltonian vector field. You don't need to know what is structurally stable Hamiltonian vector field, but just consider 2D fluid. Okay, so just 2D fluid, and then it consists of the following finite number of components. Sorry. I mean a two-dimensional fluid can be, any two-dimensional fluid can be decomposed into combination of a finite number of components listed below. And okay, so you do not need to understand the terminology. These terminologies are from dynamical systems, but the classification detail is not important. And the point is that we can decompose a fluid flow into a combination of some components. So we can make correspondence in this way. So we can assign a label, an appropriate label to each component. Also, we can assign orientation signs plus or minus. I mean, if a fluid flow is counterclockwise or clockwise, then we can assign a label. I think so. Is right. Also, we can translate the nest relations of streamlines into the tree structure. So, I mean, for example, you can see here the streamline here. Look at this streamline here. It goes from this boundary point D, then follow this streamline E, then go back to the boundary. And inside this streamline, we find a periodic orbit, right? Right. This orbit G is periodic, right? In such a way, in general, two-dimensional fluid flow can be decomposed into such a way, like using nest relations, right? So orbit types, orientation, and nest relations. And considering these three, we can translate the streamline topology into tree-structured language. Okay, so this is what we call a partially cyclically ordered rooted tree, abbreviated as TOT. By the way, if you have any questions, please feel free to ask me, interrupt me. Yeah. Okay, so I will show you some definition of the labels. So this is root labels. Okay, so first one is a node. A node denotes the unbounded and uniform flow. Okay, if a fluid, two-dimensional fluid is unbounded and uniform, then we assign this label A node. Okay, and if the flow is bounded and rotating, then we assign this or this label beta node minus or beta node plus. Okay. And in this case, we have counterclockwise rotating flow surrounded by the wall. Okay, and if we have this clockwise rotational flow surrounded by the wall, then we assign this label beta node plus. So these three, we have these three root labels. And you see some box here, some box with labels, box with some boxes. And for example, if we see this box A here, there are some numbers of box A. We can nest other symbols of type A here. I mean, for example, we may have such kind of streamline pattern inside here. Okay. And in this case, topologically speaking, this pattern is denoted by, so this is counterclockwise. So counterclockwise case is this one. So this corresponds to A naught A plus. We may also have negative pattern. I mean, we may also have this kind of dots. This kind of clockwise eddy flow. If we have a clockwise eddy flow, then we assign the label A minus. Okay. In such a way, we can construct a tree-structured language like this. So there are also B types and C types. Okay, so I already presented type A, and type B is vortex eddy. So this is a twin vortices, a pair of vortices. So there is two vortex like this and like this. Both are counterclockwise, so we assign plus signs. And this pattern has both negative clockwise orientation, so we assign B minus minus. In such a way, we assign these labels B plus plus, B minus minus, B plus minus, B minus plus. And if we have an obstacle in the flow domain, then we assign this beta plus or beta minus. If we have obstacles and rotating flow around the obstacle, then we assign this beta plus or beta minus. And pattern of type C corresponds to the boundary flow. So look at this. We have boundary of the object obstacle here, and the flow comes from this boundary, then goes back to the boundary again. Then we assign C plus. So this boundary to boundary streamline corresponds to C plus, and this pattern corresponds to C minus. And again, we may have, for example, we may have this H-shaped streamlines here or C minus streamlines here, or so on. Okay. So we may consider any combination of these patterns, type A, type B, and type C. Okay, so this is a short, brief introduction of the COT representation. And COT representation actually corresponds to a so-called Lev graph. Lev graph is a mathematical object coming from geometry. I think the mathematician Lev first invented, I think. And Lev graph encodes nest relations of contacts like this. So it has something to do with our COT construction. So in the algorithm, we first construct Lev graph, then convert it into COT representation. But I do not talk about the Lev graph part. When I talk with mathematician, I talk a lot about Lev graph, but I skip this chapter today. If you are interested in the Lev graph chapter, then please ask me later. I skip this chapter today. Sorry. So, are there any questions at this moment? Okay. So, I want to move to application chapters. So let me first introduce application of our TFDA method to meteorology. Meteorology. There is a so-called blocking phenomena in meteorology. And this work is joint work with Professor Inatsu in Hokkaido University. And okay, so do you watch weather forecast in TV? Okay, you see this kind of pressure field plot in weather forecast, I think. But rigorously speaking, I think that pressure field responds to so-called geopotential height. And I think this geopotential height can be observed somehow by a satellite camera or sensor. I don't know the detail, but anyway, geopotential height can be observed and reconstructed by, I think, some numerical model. Anyway, it approximates the pressure field. So what we see in the weather forecast is this data. Okay, and if we convert this pressure field to red graph and then COT representation, we can obtain this kind of this kind of COT representations. You see A node, A minus, B minus, minus, and so on. Right? And we applied our TFDA and COT representation to this meteorology data. We proposed new index for detecting blocking phenomena. What is blocking phenomena? Well, blocking phenomena is so if a certain pattern of high pressure or low pressure persists for long days. Let's say if we have a high pressure region persists for a week, then it affects the weather temperature a lot, right? So it is a very interesting topic in the meteorology. And in meteorology, there is this classification of blocking phenomena. So first one is dipole type, and second one is omega type. And in our TFDA language, this can be said like very simple way. I mean, a dipole type is a pair of high pressure region and low pressure region, but this can be expressed in our TFDA language as just A minus and A plus, right? So because we have so this part is counterclockwise and this part is clockwise. Okay. So this pair of vortices corresponds to the dipole type blocking. And there is also omega type blocking. This pattern is called omega type blocking because this streamline pattern looks like the Greek letter, right? Greek letter omega. And this is expressed as A plus in our COT package. So typically such local pressure patterns persist for more than 4 days. Then we say it's blocking. Strictly speaking, there are no rigorous or standard definition in meteorology. I mean, there are several definitions for blocking phenomena. So, but anyway, we typically say that it is a blocking phenomena if such kind of patterns persist for long period. And our TFDA index can quantitatively evaluate persistence of such patterns. So let's say if we have A plus pattern or A minus A plus patterns persist for more than 4 days. So this is a histogram of persistence. We convert the TFDA result to histogram. How long such patterns persist. Then the red region corresponds to the 4 days. I mean, so it is something like blocking phenomena. And I do not tell you the detail about how we detect the blocking phenomena in our method. I mean, we also use certain a priori knowledge from meteorology. I mean, nose area and enough large, then we judge it as a blocking phenomena and so on. But anyway, we can detect blocking phenomena algorithmically. And this result is sufficiently well compared to the existence method to judge the blocking phenomena. Okay, so then let me talk about application of TFDA to oceanography. In oceanography, there is so-called cross-shore mandering. Cross-shore mandering is also how to say, responds to the persistence of an eddy flow. So we can apply our TFDA method. And the basic idea is similar to this meteorology application. So it's a nice movie. By the way, this work is collaboration with Shun Oishi from Riken, and he's a specialist in oceanography. And here's a nice movie. And I think here you see, Japan, and here, and you see a cross-shore mandering. So this is cross-shore mandering. Japan part is short. Okay, anyway, so we see various ocean currents and eddies in this movie, and actually, cross-shore mandering is, cross-shore current is one of the fastest current over the global ocean in the world. So I think it's about 2 meters per second. The velocity of the current is very fast. Right? Surprising to me that the sea water goes such fast. But anyway, so this ocean current affect heat and moisture transport. So it also affects the fishes. I mean, so it affects the fishing result or so on. So this is also a very interesting topic, especially in Japan, because it affects fishing. you like sushi, so so this current affects a lot. So okay, so there is a so-called color-based classification of cross-shore mandering. So first one is Rajimander. Rajimander means this. So this current goes from this to then mander, then go this way. So this pattern is called Rajimandering, right? Because this part is very large mandering, right? And there is also NLM. NLM is a near-shore non-Rajmander. So near-shore, right? Near-shore and mandering is not large. So this is called near-shore non-large mandering, NLM. And there is also offshore non-large mandering. So this kind of offshore, and this is not quite large. So this pattern is classified as an offshore non-large mandering. And we apply our TFDA to detect this mandering. I mean, so this part, we see this kind of A minus pattern. So we can detect cross-show mandering by looking at this A plus minus labels. And actually, so this plot, look at this plot, and the red one is a report by JMA. JMA is Japan Meteorology Agency or something like that. I forgot the correct name. I think it's 気象庁 in Japanese. Japan Agency, oh no, Japan Meteorology Agency. So Japan Meteorology Agency reports this cross-show southmost position plot. So this is the cross-show southmost position. So I mean, so this part. So this, and our TFDA method also can calculate a similar one. I mean, this southmost region of this A minus pattern. Right? Southmost region of this A minus pattern. And they correlate very well, right? Correlation coefficient is like 0.99. So TFDA index can evaluate persistence of eddies of Tokai district very well, and also eddies southmost position coincide very well with JMA's report. And also in our analysis, the patterns, two patterns, NLM and LM, can be distinguished, right? Distinguished by looking at this A minus region. If this A minus region is large, then this is large mandering, and if this A minus region is not large, then it is not large mandering, right? Very simple definition. So we also can do scenario analysis. So cross-show mandarings is a very, how to say, long scale phenomena. It persists like years or months. So, but sometimes cross-show mandarings terminate. So when does it terminate? We do not know when it does terminate. I mean, cross-show mandarings persist for very, very long time. Then sometimes it ends, and we find that this scenario happens around the time of termination of cross-show mandering. I mean, we have this cross-show mandering first, then sometime this twin vortices is generated, right? This twin vortices generated inside the cross-show mandering. Then we should have certain structure transition, topological structure will change. Then these twin vortices are split into this A minus pattern. Then the small one flow away, right? Small eddy flow away to which direction? It's east. The small one flow away east. Then we have smaller mandering current, right? So this pattern is observed in real world data. So, for example, this is from 2019 April 2019. We find this A minus B minus pattern around this Tokai district. Then after 1 month, we find the A minus pattern. So we have this B to D transition. So this is very interesting because in the JMS, report, they do consider very, how to say, physical quantities and physical models, but our method does only consider topology of streamlines. We do not consider any physical quantities, only topology of streamlines, but we are able to observe such interesting properties in the ocean flows. So I think I do not have enough time, but let me try to talk about the third application part. So the final chapter is about lid-driven cavity flow. Lid-driven cavity flow is a typical test bed problem in numerical fluid dynamics. So I think I do not have time, but anyway, we consider this kind of numerical simulation result. And so we have a stream function from numerical simulation data, then we convert it into red graphs, then we convert it to hot representation, just like the previous studies. And so what is lid-driven cavity flow? Well, lid-driven cavity flow is a very typical, well-known benchmark problem in numerical fluid dynamics, and it has some interesting properties. I mean, so there is a so-called Reynolds number, and when the Reynolds number is low, then we can find no non-trivial steady state in the lid-driven cavity flow. And if the Reynolds number becomes high, then gradually we can find vortex interaction, vortex attachment and vortex detachment from the boundary of the computational domain. I skipped this part. This is how my collaborator did. Collaborator Matsumoto-san, Professor Matsumoto did numerical computation. And we obtained TOT representations from data. And again, hot symbols nested like this way. Then we obtain this hot representation. COT is like this. Okay, so in this case, it's beta node minus. It implies clockwise rotational flow, and we have boundary streamline here. So C plus, and in this part we can find C plus. Here we have C plus, and we have B plus plus. We have this nest structure. In such a way, lid-driven cavity flow, time series data of lid-driven cavity flow can be converted to time series data of COT representations. It's a discrete dynamical systems, so-called discrete dynamical systems in mathematics. Anyway, so we can do transition analysis. I mean, we have a time series data of lid-driven cavity flow, and then we convert it to a time series data of COT representation like this. So this is C plus, C plus, C plus, C plus, B plus plus, C plus, and so on. So this is a reduced order modeling. So the original fluid data has very high dimensional degree of freedom, but in using TFDA, we only look at the topology of streamlines, so very reduced order model is obtained, right? And So let's change the Reynolds number and let's see what happens. So if the Reynolds number becomes high, the transition diagram becomes complicated. So when the Reynolds number is small enough, we have very, how to say, periodic transition. But once Reynolds number becomes very high, transition diagram very complicated. Sorry, this slide is between Japanese, sorry. But anyway, so we can observe that how Reynolds number and the topology of streamlines respond. Okay. Okay, so let me summarize my talk. I think it's almost end time. So I presented the very basic idea of topological flow data analysis. And mathematically speaking, streamlines topology is classified, and we convert this combinatoric structure into three language called cyclically ordered tree, COT representations. And today I have presented three applications. And three applications. First one is meteorology, blocking phenomena, and second one is oceanography, rendering, ocean rendering. Okay, so it is very interesting that we only consider topology, the shape, rough shape of streamline plots, only streamline plots and topology, but we can observe many physical phenomena. So it's very interesting that the topology and such physical phenomena relate. So this is a very interesting point of our topological flow data analysis approach. Okay, so thank you for your kind attention.